Vertical uniform circular motion. Have you ever been in a car or a bus that went over a bump or into a dip? Do you remember feeling slightly lighter or heavier than usual? This is not a trick of the mind. When you ride over a hill or into a dip, the normal force exerted on you by your seat changes how heavy you feel. This feeling of heaviness or lightness is your apparent weight. It is due to a change in the normal force acting on you. Apparent weight is often what we draw on our free body diagram as the normal force. It opposes the downward force of weight. It's the force pushing up on an object by a surface. When that becomes zero in the vertical direction, the object becomes weightless, and I put that in quotes because you still have gravity pulling down on you. That means the object's apparent weight is zero, not that the force of gravity is zero. Gravity does not go away. Airplanes can fly in a way that changes the apparent weight of its passengers. Passengers can either become weightless, again with the quotes, meaning that their apparent weight is zero and they're just kind of floating around in that airplane. The top of a hill, shown over here, can be viewed as being part of a circle, so the car's path is circular at that point. Assuming constant speed, it is in uniform circular motion as it goes over the hilltop. In the diagram, the hilltop is the top of the red dotted circle over here, okay? And the blue dot is the car. Its velocity and centripetal acceleration are shown as black and green arrows. So here's your centripetal acceleration, here's the velocity of the car. Draw a free body diagram of the car, making sure to include its weight and the normal force acting on it from the road. Next to your free body diagram, draw the direction of the acceleration. This shows that the normal force is pointing up. That's the ground pushing up on the car. The weight and acceleration are pointed down. And here's your acceleration vector. There are no horizontal forces. Now, use Newton's second law to write an expression for these forces, making sure that the signs for the forces and acceleration are consistent. So here's plus over here, here's minus. Sum of the forces is ma. Both the acceleration and mg point in the negative direction, while the normal force points in the positive direction. So this is positive, negative, and negative. Add mg to both sides. Substitute the expression for centripetal acceleration as the car is briefly in UCM as it goes over the hill. That's this term here replacing a. Since the normal force provides the feeling of weight, this equation that shows while the actual weight of the car is constant, this mg here, its apparent weight is less than its actual weight. Now that's when it's moving along the top of a curved path, right? Because you're subtracting this term from mg. The force of gravity is greater than the force of the road pushing up on the car. Therefore, the net force acting on the car is pointing down into the ground. In fact, the car becomes weightless when the normal force is zero. Let's solve for the exact velocity at which the car would be weightless. At that speed, the car will lift off the ground just slightly, so the road won't be pushing up on the car at all. So we start up here, and first thing we do is set the normal force equal to zero, then solve this equation for v, and here's one step, and then the masses cancel out. G is v squared over r, and finally we get v is the square root of gr. This is the velocity at the top of a circular path when a car and its passengers become weightless. At higher velocities, the model breaks down since the car would fly off the hill, but the normal force would still be zero. The normal force cannot be less than zero. Now we'll determine the apparent weight at the bottom of the circle driving into a dip in the road. So here's a car coming into a dip. Also, roller coasters do this, of course. Assume that the car maintains the same speed it had when it went over the hill. But while still pointing towards the center of the circle, the normal force is now opposed to the weight of the object. So we'll get a different result. The passengers will feel a different apparent weight. Once again, draw a free body diagram. Make sure to include its weight and the normal force acting on the car from the road. Next to the free body diagram, draw the direction of acceleration. This shows that the normal force and the acceleration are both pointing in the positive direction towards the center of this circle. Again, the car is only doing this, but it's got a piece of a circle, and we're still having it point towards the center if we extend the circle out here like we did. The weight mg is pointing in the negative direction. There are no horizontal forces. Once again, use Newton's second law and make sure that the signs for the forces and acceleration are consistent. A, the acceleration, is now positive as it's pointing up. When the car was on top of the hill, A was negative. The normal force is positive and mg is negative once again. We put in our correct signs here. Solve just for the normal force, and then once again put in centripetal acceleration for the A. Since the normal force provides a feeling of weight, the equation shows that while the actual weight of the car is constant, mg, its apparent weight, the normal force there, is more than its actual weight. That, again, is when moving along the bottom of this curved path here. In this case, the force of gravity is less than the force of the road pushing up on the car. Therefore, the net force acting on the car is pointing up in the air. Let's solve for the exact velocity at which the car would be twice as heavy. At that speed, the car's apparent weight will be twice its normal weight. So we start with our normal force, the equation we came up with in the previous slide, but this time, what we're going to say, the normal force will be 2 mg, not 0. The car this time is pushing down into the road with twice the amount of force. So we have mg plus mv squared over r equals 2 mg. We solve for v. Then we have v squared over r equals g, a little more algebra, and v is the square root of gr. So a car moving at exactly this velocity would be weightless at the top of the curve and be double its weight at the bottom. This equation, v is the square root of gr, gives the velocity at which an object becomes weightless at the top of a circular path. It is also the velocity for doubling the apparent weight at the bottom of a circular path. The mass of the object is not in the equation. A truck or a bicycle going over a hill would feel weightless at the same speed. Have you ever seen someone swing a bucket of water over their head and the water stays in the bucket? A bucket on a rope moving in a vertical circle is another example of circular motion. The forces acting on the bucket are the tension in the rope and the gravitational force of the earth. First, examine the bucket when it is at the bottom of the circle. Once we draw the free body diagram and apply Newton's second law, we have the sum of the forces is ma. We've got tension in the up direction, which is positive, just like the acceleration, and gravity is down, so that's negative. Depending on what is given, this equation enables the finding of the other values. Slightly trickier to figure out is when the bucket is at the top of the circle. You might think there is a force pointing upwards as none of the water is falling out, but there is not. Two forces, tension and mg, both point downwards towards the center of the circle. Water will not fall out as long as the bucket has a large enough tangential velocity. So draw the free body diagram. Here it is, tension and mg going down, as is the acceleration. The natural tendency of the bucket and the water in the bucket is to go in a straight line to the right, tangent to its circular motion. But the rope is pulling down on the bucket, causing it to travel along the circular path. The bottom of the bucket is also pushing on the water, forcing it into the same circular path. Just a quick aside here. Force does not tell us which direction an object is moving. It tells us how the velocity is changing. Right? Even though both forces are down, the bucket is not going to follow that direction. So here's our sum of the forces. We've got tension and mg both pointing down. The acceleration is down. Do a little algebra, and we come to this over here, where the normal force plus mg is mv squared over r. The minimum velocity for a bucket to make it around the circle is achieved when the tension in the string becomes 0 at the top of the circle. So see, there's no tension here anymore, and the rope is kind of going to do something like that. If the tangential velocity of the bucket exceeds v is equal to the square root of gr, then the water stays in the bucket. And we derive that right over here. We got rid of the normal force. If the velocity is less, then the tension in the rope is 0 and the water falls out of the bucket. A roller coaster car going around a loop works exactly like a bucket on a string. The only difference is that instead of a tension due to a rope, there is a normal force exerted on the car by the roller coaster tracks. So the roller coaster car here is inside the tracks, so the people are going to be upside down. When the roller coaster car is upside down at the top of the loop, the tracks are pushing down on the car, forcing it to move along a circular path. When the car is at the bottom of the loop, the tracks are pushing up on the car. Take a minute to calculate the minimum velocity necessary to keep the car moving through the loop at the top. To find the minimum velocity, set the normal force equal to 0. At that exact moment, the car isn't pushing up on the tracks anymore. It would start to fall if there weren't a whole bunch of safety features here prohibiting that, but we're just going to assume we have a test dummy in there. And therefore, the tracks aren't pushing down on the car. The only force acting on it now is gravity, and it's in the down direction. Minus mg equals minus ma. Then we solve the algebra, replace acceleration with centripetal acceleration, and we find the same minimum velocity for the bucket on the rope or to feel weightless while driving over a hill. It's a cool thing about math. One set of math equations solves many different physical problems.